If you are new to graph neural networks, please watch the first video, because in this video, we're gonna have a look a little bit deeper into GNNs. You're familiar that last time I told you about that data can be represented either in a grid structure, like say example, if you have taken a picture and all the pixels are analyzed by some vision neural networks, or if you work in NLP, in natural language processing, and you have a sequence, the data are structured in sequence of words, in sentences, in paragraphs, in books, in whatsoever, in your natural conversation that you have. And we touched on the subject on graph neural networks. Now, graph have a more complex topological data structure, and machine learning graph neural networks is a challenge. So let's dive deep into this. I have here found a very nice internet source. It's called DistillPub 2021. As you can see, all the authors are all from Google Research, their affiliation of Google Research. It was published in September 2021. And it is about graph neural networks. Now, graph we told about, we have vertices, we have edges, and we have the global structure of a graph. We find graph, as I already told you, in images. You can have here the adjacency matrix, you can have the graph. This is a very nice interactive presentation. I would recommend you go to this page and have a look at it yourself. As I told you, you have a sequence of words where you have graphs all around us. You can have here a very simple adjacency matrix if the words are your encoding. But then, of course, and I told you already in the last video about the molecular simulations where GNNs have been applied successfully. If you have a topological ring structure, a two-ring structure, we talked about social networks as a graph, and the graph, we have the task that we want the GNN to perform is, let's focus on two. We have a node level task and we have an edge level task for the beginning. Now, the node level task is easily explained. You have here a representation of persons. Let's say it's a class of people, and they have two instructor person number 1 and instructor person number 2. And as you can see, there's a graph with some links. Now the nodes represent person. You can see this is a significant person, and this here is a significant person. This might be a significant person. And the task is, if you now split up this group, this set of persons, and you have a connectivity of this person to person A, and you have a connectivity of this group to person B, how would this group split up? Now, very easily, as you can see here, let's say this person Z here has some edges, whatever they are, does not matter at this point, to two members of this set, and both members have a connection here to this important person A. So with a high probability, we can see visually that since this person has only a connectivity to those two persons who belong to this subgraph, to this subset, to this people, to this group of people, it is highly unlikely if you decide, will this person, when these two super persons split up, will they join this group here? No. Since he knows these two persons and both persons belong to this subgroup, we can say, okay, this person will join here, the red group circled around Mr. He. So we can see it is human, but how do we teach a neural network to perform this task for us, also to higher complexities, not just in a two-dimensional planar representation? The other thing is edge. Edges are, if you want, correlations. You have here a fighting, you have here a judge. The judge is watching both players, player A and player B, and player A is fighting player B, and of course the other one is fighting the other one. So these are the correlations between them, watching, standing on, fighting, whatsoever. And now you want to predict one edge. Is there an edge between two entities? Yes or no? So these are our two tasks, edge level task and node label task. And now we start with graphs in machine learning, geometric deep learning. Now let's start with a very nice and simple example. But before this, some definitions. So why do we use graph neural networks? Because we want to make predictions. We want to solve graph prediction tasks. And I showed you an example. We want to know if person Z, does it belong to group A or does he or she belong to group B? So we want to have predictions about this complex data structure. And a graph neural network is nothing more than an optimizable transformation on all the different attributes of the data, of all your nodes, of your edges, and of the whole graph in itself. And of course, you know that systems that preserve symmetries are the most important system also in physics. And we have a GNN that preserves graph symmetry, permutation, invariance. And now if you look at this and you want to understand it, there's a very nice example. Your input to a GNN is a graph, and your output is a graph. And what you want to achieve is an embedding of all the parameters of these graphs, of the nodes, of the edges, or of the graph itself, that you achieve an embedding with a vector representation, if you want, in a specific topological space, that you then can say, okay, I have now, let's say, a classification layer, a softmax operator, and you can say, okay, this belongs to category A or category B. So a very clear node label classification problem, a prediction if the node belongs to group A or group B. And there's a very nice presentation if you go there and you start to understand it without applying the full mathematical apparatus to this problem. Pooling. How do I explain pooling? Let's have a look at the structure, at the edges. What can the edges tell us? And here we say, again, have the case of a binary classification. So is it A or B? And it can be extended, yes, of course. And the task is to make binary prediction on nodes. And the graph already contains node information. The approach is straightforward, as we have seen with a linear classifier on the embedding. But if we do not take the node information, if we have information in the graph stored in edges, but no information in nodes, we still want to make prediction on the nodes. So how we do this? Now the answer is pooling. We need a way to collect information from the edges and give this information to the nodes for a prediction, for the prediction task. And we can do this by pooling. Now the pooling algorithm in itself is kind of a topic of ongoing research, how to optimize this and whatsoever, but it is a very nice presentation. I would recommend you have a look at this yourself. And the end-to-end view of what we want to achieve is, we have an input graph, some data structured, well, data living on a graph with relations between the data points, some edge weights and whatsoever. And we want to make a prediction. Hey, is this person here, does it belong to group A or B in this graph, as I already showed you? So you build, you stack your graph neural network blocks, your layers together. You achieve a transformed graph, an optimized graph. The embedding, you have a classification layer, can be a very, very simple softmax, for example. And then you have a prediction. And either you have the object is the node, the edge, the global prediction, you can have a message passing, neural network, whatever you apply. You want to get a result, A, it belongs to A or B. So this is a very simple GNN model, a very simple graph neural networks. Now, message passing, very nice presentation, have a look at yourself. if you want to learn a little bit more about the structural data. But the focus now in this video is how can we program this? We want to encode all of this information we were talking about now finally in code, in Python code. I want to show you today how to do this following the official KERAS library, node classification with GNNs, and we will follow here this example. Now, as you can see here, we have, or I will give you the link of this Google Colab notebook, where you have all the code sequences already done, ready. You just copy the notebook, the Jupyter notebook, and you can experience the code for yourself. I would like to show you, or go with you through the code sequences and trying to understand together with you what the hell is going on here. Of course, if we have done this, you might say, hey, are there not some geometric libraries? And of course, and there are two libraries I would like to show you in the next video. One is PyTorch Geometric. It's a library built upon PyTorch, and it works in PyTorch, of course. Or if you prefer, there's DGL. This is a deep graph library, and it is framework agnostic. This means you can operate it on your PyTorch or in TensorFlow. So this is, if you want to be on the safe side, TensorFlow or PyTorch, this is great. The install is very easy. You can select whatever you are, and then you have your conda install DGL team DGL command, and it is installed. So very nice. Of course, PyTorch Geometric also available if you want to stick to PyTorch. But our task today in KERAS and of course TensorFlow is to run through the process together. So let's have a look at this. We have here the bare bone. We have an introduction. We prepare our data set. We download a data set. We do not create our own data set. We split the data set into training and the test data set, as you know it from the normal neural network, the train and evaluate experiment, and you create a feed-forward network module. And this module you can use. Just for Jack, we have a baseline neural network model, and you build your graph neural network model. So you prepare your data for the graph model. You implement a graph convolution layer. I was talking about the convolution. You're familiar with this from vision, from the vision area. You implement a graph neural network node classifier. So this is what we have been talking about. We have a node and want to classify if a particular node belongs to the group A or to the group B. If we have a binary, then we train our graph model, and then we examine the accuracy of its prediction based to a normal baseline model, for example. So this is the process we want to run through. As I told you, the notebook is available for you to download. It was created in mid-2021, so we are about 4 months after the creation of this notebook. This presentation, as I told you, is done in September, so we are 2 months behind this. And the interesting part, of course, is let's try to understand how to code this model. We use TensorFlow, we use KERAS, but of course, afterwards, as I told you, you can use much faster, much more elegant PyTorch Geometric or DGL for your tasks. So here we go. At first, we know that we have to implement the graph convolution layer from scratch. We import our libraries. We have NumPy, we have our pandas, we have network X. This is the classical, if you want, network graphs toolbox. Our matplotlib, we have TensorFlow, we have KERAS, and we have our different layers. Now, the core data set that we're going to use here consists of 2,700 scientific papers, and they are classified into 7 classes. And the network has more than 5,000 links. Each paper has a binary word vector indicating the presence of a corresponding word. You download the data set, you prepare your data, you can visualize your data set, you have the target and the source data set, beautiful. You have everything you need. Display the kind of the papers. Here we go. We have neural networks, 800 18 papers, probabilistic methods, 400 papers, theory, base case, reinforced learning, and rule learning. Okay, so we have our categories. Great. And if you want to have a visualization of the subset, this is of course just a subset of all the papers, you can see here. I suppose the dots are the papers, and then of course the edges represent the citation, which paper cites what paper and gets recitated. You split the data set in training and test data set, and you are familiar with this. You define your hidden units, your learning rate, your dropout rates, the number of epochs you want to train the system on. You have the typical KERAS atom optimizer. As a loss function, you have a sparse categorical cross-entropy loss function, and of course you run with ACC. You have your callbacks, your early stopping procedure, and then you train the model. You have the number of epochs, the batch size, the validation split, the callbacks, everything you are familiar with if you put in a model in this definition of this particular function we call run experiment. And then of course you want to know how good does it perform. You have a display of the different performance curves. And as we already said, we implement a feed-forward network model we use as in the baseline neural network model and in our graph neural network. So let's switch for the graph neural network because this is the interesting part. And here it gets immediately non-trivial. So prepare the data for the graph model. And the graph data is represented by a tuple, which consists of 3 elements: the node features, the edges, and the edge weights. And as you can see here, it is beautifully defined. But now comes the interesting part. We implement a graph convolution model as a KERAS layer. So this is really now the code how you implement on a GNN a convolutional layer. Yes, the techniques implemented use ideas from the graph convolutional network, the isomorphistic network, the simple graph network, the gated graph sequence neural network, the graph attention networks, of course, and the message paths and everything. So heaven's sake, the next important thing is we need, as I showed you, a graph neural network node classifier. We have a task, we want to classify, hey, person set, does it belong to group A or B? We want to classify the node that this person represents. And here we have a certain procedure, and this procedure here is highlighted for you in a specific publication in Archive, Design Space for Graph Neural Networks, and this is from July 2021. And heaven's sake, they defined a design space and they have, where is it? 3 tasks. If you really want to understand this design space for graph neural networks, Stanford University, I'm sure it's an interesting topic to read. But now, for me, trying just to understand the basic structure of all of these code sequences, I go on with my 4-step methodology here. So, pre-processing using my feed-forward network to the node features to generate some node representation. Then I apply my graph convolution layer to produce my node embeddings, exactly what I want. Then I train it, I generate my final node embeddings, and then I feed those node embeddings in a softmax layer, whatever discriminator you want, to predict the node class. This is exactly what I showed you before. And take, here we are. This is our classification layer. This is now a softmax layer. And then we have a simple prediction, yes or no. So this is performed here in this step. And if you want to have here the code for the node classification, heaven's sake. So enjoy this code. This is it. If you really want to have the nitty-gritty in detail, and then you have the model, you can provide the indices, you have your classifier, your graph info, your classes, your hidden layers, your dropout rate, and whatsoever. This is now your GNN model. Then you train, you know we have defined a function run experiment. with this GNN model, with your data set, with the training data. And after you executed all the different steps on a Google Colab notebook, heaven's sake, you have your learning curve, you have your performance parameter, you have your test accuracy, 80%. And now finally we have a trained model, and we can now have some new data input and have some predictions on this. And here's the code to do it. Update the node features and edges and whatsoever, and then you get here the prediction of the trained graph neural network. Heaven's sake, today it was kind of complicated. I'm sorry for this, but it is, of course, I leave you the code for this Jupyter notebook. You can run through all the code execution yourself. You can optimize the code. You can play around with it. No problem at all. It is TensorFlow. It is based on KERAS, the node classification with a graph neural network where all the data live on a graph, have a graph structure, and not, as you are maybe familiar with, a grid structure or in NLP, a sequence structure of the data. But this is it for today, the node classification with graph neural networks. Heaven's sake, we made it through the process. Congratulations! And if you stick with it and if you're interested, I would like to show you in the next video either the PyTorch geometric, there are some beautiful, simple examples, or we go for agnostic structure that you can operate either on PyTorch or on TensorFlow with the deep graph learning library. And in any way, finally I'm able to tell you, I see you in the next video.